a castle on the hill. Oh, oh. Good morning. So I think what I really want to do this morning is try to figure out where, what's up with this. I think really it's easy. I just am looking at this kind of in the wrong light. Now, let me find what. Let me figure this out here. I'd really like to figure out where. Okay, so here are the operators. But it's interesting because what I think really what I want is to kind of house some Euler angles. Euler, sorry. Euler. It's a bad habit that I've been trying to break. And we're gonna port. This is a C++ method I used. And what we're gonna do is port. We're gonna port it. And I think I'm just gonna add some. Just gonna add a util. I'm gonna add just like a static method or static class, like let's just call it math extensions. I don't have anything pulled. Let me get the chat pulled up and all that good stuff, because I do not have that open. All right. So let's get rid of the annoying. And this needs to be public static. And let's just so Extension helpers for math-based objects. All right, so here's our conversion here that we're going to port. And so what we actually want this to be is we want this to be a public static. We're going to return a quaternion. And we'll do float x, float y, z, and really we could probably call it, hold on. Actually, this is silly. Since this is an extension, I want to do from vector 3. So I haven't figured out if we're doing conversions from degrees to radians or not, but I should probably glance at that right now, actually. So let me open this. Let me open this guy up and see. Let me see. Like if we, I know like Quaternion has like a. Sorry if it's not showing the right. It's not. Give me a second. Just need to find methods and like maybe. Let me find like there's lerp and slurp and squad and spline and. So yeah, I think all of this is supposed to be in radians. Okay, so that's fine. That's good. That just means we don't have to convert it. So we'll just do float phi equals this dot x times 0.5f, and then theta is this dot y times 0.5f, and float psi equals this dot z times 0.5f. And this, believe it, just took me so long to like find out how to, because Euler angles and how it's how you propagate each angle through the system is kind of up to the implementer. But I had an idea of how I wanted it to work, and so when I was prototyping this thing, this particular function, I remember taking me forever to come up with the correct combination of pluses, minuses, and angles here. So actually though, yeah, so God, that's really annoying. That there's only, so I guess, did he use sine? Did he use the math? Yeah, he just returns everything as a float. I got it. Okay. So we can actually we're gonna recreate this stupid macro here that I have, and it's probably gonna make it pretty expensive, but we shouldn't be using this. Well, I digress. I don't know. We may be. I'm not gonna go any further than that. Private static. This will be a float angles, and we'll pass it. It's gonna be it'll be a func double func double func double. So these are gonna be our representations of our math functions. We'll call this like F1, F2, and F3. You'll see why it kind of behaves the way it does in a second. Actually though, you know what? Let's define it in here. Make it like a closure, because let's see if I can do that. Let's do this. Private static delegate. Whoops. Float. Let's call it angle delegate. I wonder why it's mad at that. Oh, can't. No need for static. Forgot about that. Okay. What's up, man? This is gonna be somewhat of a slightly shortened session today. I want to try to do this, and then I want to try to do some texture stuff, and then I gotta get to work. But let's see. Basically, we want for this our angle delegate. We'll just call it angles, and we'll say equals ABC. That's going to be our funcs. And the way this is going to be replied is we're going to return. How do we do this? What was our this is going to be really ugly. Let's see. Actually, so we're going to return float A phi times float B theta times float C theta. Oh, nope, C psi, I think. All right. Yeah, believe it or not, actually, I can even shorten that just a tiny bit more. We can remove this and just have this. And so when we do we no longer need like a macro. We can just do, we can do float x equals angles math.sine, math.cosine, math.cosine, minus angles math.cosine, method sine, method sine. Yeah, thanks. That's why Unity adds math F. Because of that exact same reason. Float z equals angles. I did have a sine issue there. There we go. Sine, method sine, method cosine, and then float q or w equals angles. That cosine, method cosine, method cosine, and then plus angles, method sine, method sine, method sine. Really and truly, we should just multiply it out all out. And actually, now that I'm looking at that, I think we absolutely should. But I don't want it to be, yeah. Anyway, it's math functions are ugly. They always are. And then we'll return new Quaternion. X, Y, Z, and W. Yeah, I mean, really and truly, we don't want to have to apply this multiple times. I mean, this is really inefficient. So maybe we should optimize it a little bit, because I think the way that I'm going to use it probably is not yeah, let's see. So so this is going to be awesome. So sine phi. Float sine theta. Float sine theta. Float sine psi. Float sine. I don't think so. I think that something has to be using as a resource acquisition thing. It's not a syntax sugar. What's up, Bo? Cosine phi. And then cosine psi equals float math dot cosine psi. All right, so we can get rid of this. Don't need this. Don't need this. And so what we actually need now is this is sine, cosine, cosine. So this is, I'm just going to do them all out one at a time. So sine phi, cosine theta, cosine psi. Okay, there's the first one. Second term is cosine phi, sine theta, and the third term is sine psi. Okay, that's x. Y is cosine phi, sine theta, cosine psi. And then sine phi, cosine theta, sine psi. Yeah, it's way better because we're not actually applying the function every time. And that would be why. Not just, I mean, the macros, even with the macros, like in C++, like that was a really inefficient. Yes, absolutely. It should be way faster. Third term is cosine phi, cosine theta, sine psi. I mean, it's actually just trying to work through the conversion here that's kind of difficult. Sine theta, I'm going to have to make sure I don't make any typos, and psi. So it should be phi down the first column, theta, and then psi. And it looks like it is. And it goes, here, we'll check it at the end. Cosine phi, cosine theta, cosine psi. And then sine phi, sine theta, sine psi. Okay, so it should go cosine sine, cosine sine. Oops. Actually, let's do this. Let's just go ahead and start like putting these together in terms. So minus, minus, and then this whole term. So float x, and we could probably reduce this into, and I could probably, those aren't necessary, right? The parens aren't necessary here. I don't think. God, this is, I can't look at it like that, man. It's too scary. It's too scary. I don't think that they're necessary, but we're going to put them there for clarity because otherwise it's horrifying to think about. Also, I think it makes the minus a little bit more it makes the other operator a little bit more obvious. It's got to be a faster way to do this. Minus, and then this whole thing, and then this whole term. And then float W. It's a lot of typing, man. Math functions, though. The worst is when you're trying to figure them out and you're doing this. It's like, and it's weird because you would think that you could just grab something off the internet, like the source for stuff like this, but it's all relative. So all these math functions are all relative to each other. So if you do one a certain way, you have to continue on. You have to be consistent. What's up, Faith? What? What's that? Yeah, it is. It's not exactly a thing. I mean, it's been up for mathematical debate forever. Like forever. But the education system always used it because it was the easiest way to explain to students some generic set of rules. But it's been up for debate for years, man. Like 20, 30 years. Okay, so this should, so those of you joining, if you are, let's see, let's call this Euler. It's Euler. This is a terrible habit of mine. Euler, angle, to Quaternion. I don't know why. It's something about Ferris Bueller's Day Off. It just makes me want to say Euler. It's so wrong. I've said it my entire life and I cannot get it right. It just reads Euler. So what we did here is so C# has this really handy extension feature, which basically lets you take any class from any library and add it has to be static, but you can add a method that will actually appear on the object, even if you didn't write it. So vector3 will now get this as Euler method. And I can show you this if we go into if we go back into our rocks object. And so I have position. We're not going to use position as a Euler angle, but you'll be able to see it in the IntelliSense here, the code completion. Position as, well, maybe not, because this freaking thing hates me for some reason. And whenever I go to demonstrate something, it doesn't work. The reason it's not working, though, is because it's in this namespace, and what I really need to have is probably have it in the OpenGL namespace. Anyway, so position as Euler. And here's the cool thing. If you look at this, this syntax, this goes away. This is actually the context. So this right here represents the vector3 instance that you're calling as Euler on. So in this case, this God, I cannot talk. I sound like I'm just like losing it here. This .x is actually, in this example, position.x. So instead of calling it like this, which would just be like a static method, it's like this. So you actually get it carries through and it adds these extension methods to the objects, and I think it's the coolest thing. Now you can't add extension static methods. And there's some there's some pretty strict rules to it. Clearly, anything that you would need to process the stuff in the function either has to be static or it has to be passed in. Well, people have argued about multiplication, addition, division, all that stuff being orderable. If that makes sense. And there are people who are just absolutely gung-ho about clarity over anything else. So like their point is, who cares about which one comes first? Just use parentheses or blocks or block quotes. Sorry, not block quotes, but square brackets, and denote which operation is a single term. Cool. All right. Anyway, so the reason that I wrote this is because this is what I want. I created these two dirty flags, one for rotation and one for just regular transform. And I think what I want to do here is I want to store store Euler angles. Euler rotation, I guess, is what we'll call this. No, I want to continue our programming discussion from today that I'm working on now. Update rotation, probably. This is where it gets tricky. I don't think that we need, what do we need force on? We need force on, what do we need force on? Transform only. Transform is the only thing that we need force on. We shouldn't have to force update this. Update rotation should just check for dirty rotation. And that's it. And this rotation matrix should just come from rotation, and this thing shouldn't be needed. It just shouldn't be needed. And I'm actually a little bit irritated that I settled for that, because that's not okay. And then rotation dirty doesn't need to be, what does that look at? Hold on. Yeah, okay. So when we look at, our rotation is not going to be dirty anymore, and our transform is not going to be dirty anymore. Essentially, that's what happens. And the thought is that whenever update rotation is called, we're going to get a new rotation matrix. And that rotation matrix is going to be applied to our lookat for the transform update. So what we actually need to do is, I want to figure out let's see. So we actually want our rotation here. So update rotation needs to actually do this. Rotation is equal to, here we go, Euler rotation as Euler. And this will return an updated Quaternion, and then we get our rotation matrix from that Quaternion. That's what we want. How actually, you know what? No, this is not what we want. This is interesting, because what we actually want is this. New, let's do this, vector 3, and we'll copy, this is what we need. We need each individual component to be the basis of the rotation. So Euler rotation x 0 0, and actually I think I can just have x maybe. No, I'm not that lucky. And then 0.0f as Euler. Okay. This is not going to be as efficient. I actually wish that let's do this. Let's add one more static helper. Let's do this the right way. So let's do math_util. Actually, and let's call this rocks math. That way I can and then we want this to be static, which just means you can't instantiate it. It can only have static methods on it. Rocks math helper. And then let's move from our extension method. Let's move this guy in here, except for we'll do this, and we'll do float x, float y, float z. And I think this is more like a yaw pitch roll thing versus a versus like a x, y, z thing, but we're going to call it this for now just to kind of z. And also it's pissed at me it's pissed because meh. We'll say X rotation, Y rotation, Z rotation, X rot, Y rot, Z rot. I forgot I had variables named like that already. And we need quaternion. It needs brackets. And that's it. Okay, so what we've done is this. Is just allow it to take 3 degrees, or radians. And our math extensions now will also public static quaternion as Euler. Same thing, right? We're going to add the same method, and we'll call it extension method, which converts Euler angles stored in a vector 3 to a product of quaternions. And I want to make this clear what this is about to do. It's about to create a rotation quaternion using each individual. So I'm going to show you. So math, or rocks math, and we're going to have to import it. Get out of here. Rocks math, using rocks util. Rocks math. And so what the first one will basically be the X. So we want to pull from this X and then 0, 0. And then we're going to multiply it. It's one of these awesome things about quaternions is you can actually multiply them, and it's just as effective as multiplying matrices. And then 0.0f, and then the y 0.0f, and then times rocks math Euler 0.0f 0.0f, and then this dot z. If you're wondering why I'm using the ampersand here, the ampersand is, sorry, I'm gonna catch up on the chat. I haven't looked in a while. The ampersand is here to basically, it allows you to use a reserved word. So like object is a reserved word, but if you ever wanted to use that as a variable name, you could do object ampersand object equals new object. Anyway, so it just lets you, and like the common one is like using like a mutex. You can do lock equals new object. So then you can do lock like that. Anyway, that's the common one. But I use it for this too because it's just helpful to see, to remember that this is like the current context that you're calling it. So let me jump into here. But if you transform a vector into a quaternion, the function name should be as quaternion. Yep, maybe. You bring up a good point there, Faith, and let me think about it for 1 second here. Let me process this, because really and truly, it's your vector 3 is typically not going to contain Euler rotations normally. but I believe, like, I'm pretty sure, and Colt will be able to verify this, that Unity's 3D's math library does conversion from vector 3 to quaternions by applying them as Euler angles as well, I think. In our case, this is really what we want. We want to consider each component of the vector 3, the x, the y, the z, as their own separate rotation that will be applied like this. So this is basically saying rotation x matrix times rotation y matrix times rotation z matrix. The thing that gets really tricky is sometimes the order at which this is applied can change. Like, I think I'm not like 90% sure that Unity does like x, z, y. So Unity would apply this x, and then they would apply the z, and then the y. But we're going to do x, y, z. That is what that is. Oh, it's an at. What is it called? What is the formal name for it? You're right. Ampersand is the and. What is the at? What is that called? If you say at symbol, I'll lose my shit. Sorry. You're right. It's definitely not an ampersand. So here's what's annoying. Here's what's annoying about, like, this is where I wish I could add static method extensions. You know what I mean? Because it really is not obvious to me why you can't. Especially because static methods don't have to meet an interface contract or anything like that. Like, it seems to me that you would be able to do that, but, you know, whatever. They don't. So maybe, so that's kind of why I added this. So this will be our, and we could probably have this as well. We could do this as well. Now, the question always, though, is really semantics, because and this is what becomes exceptionally frustrating in mathematics, and especially applied mathematics for like an engine like this, is that it is completely up to the engine to implement these things the way that they want to. Yeah, there's conventions. So the question I have, and the question I think matters, is, does this function in Unity, does it do this? Does it do this? Or does it do more of something like this? Because this is much different. And I actually think that it's probably this. In my opinion, I think that this is the way that it is applied in Unity, but it's done X, Z, Y, and not X, Y, Z. It's done in X, Z, Y order, because Unity does all that stuff like that, I think. Actually, you know what? Let's look. Let's just stop. Let's stop guessing and let's look. Because I think it's important. And I think it applies here just to show you guys, like, because when I started prototyping this thing, I thought that all math libraries would be generating the same thing, but Unity does something different. I found math papers that basically showed Quaternion math being generated like ZXY. Like, it's absolutely insane. People do it however they like, whatever makes the most sense to them. All right, I'll pull this over here. So let's see. Here it is. Euler returns a rotation that rotates z degrees around the z. And so it does it ZXY. Sorry. So the order is Z, X, Y, and it does it like this. So in my opinion here, this is what we can do. Let's return this. I need someone to tell me what the what that @ symbol is called. Yeah, you know why, Colt? Because it doesn't matter. The only part that cares about that order is unity. Internal unity. That's the only thing that's the only thing that cares about the order. I thought it was gonna be Why is it a sine? Is that a sine? Can you? Oh my God, that's so good. That's so good. So, so an Euler angle is really, a set of Euler angles is really a set of individual rotations. And to that regard, I don't even know if this is right. I kind of feel like this, like all of this work right here is just a function, but then again, I want to keep this as raw as possible. This is the math involved. This is what these things actually are. However, okay, I'm not gonna go much more into it. Let's just see if we can get this thing to do what we want it to freaking do. Because, who asked this the other day? Who asked this up here? I saw this. Let's see. So the issue with, did somebody ask about this? Problem from yesterday was the matrix 4 lookout was producing an inverse rotation. Okay. The problem with this and the problem with this lookat function is that we are pulling, so this update transform calls lookat. Okay, so when we update the transform, our hope here is that this lookat method, it works perfect for this piece. So if we are sitting in a spot and we call lookat and we give it a direction and the up vector, we're gonna look at that thing. It's gonna change our, number one, when we give it the position. The thing is for Rock's object, it's a good thing because we set our position to the existing position. Basically, if we updated this to be like, if we're at the origin and we set it to be like 333, then it would transform us, it would translate us to 333 and also look at that thing. So this is translation and rotation, because the look at part is the rotation piece. It's using that directional vector. What was happening is that when we update our transform, we just look at forward. Forward is basically using our rotation matrix. Okay, so bear with me here. Forward uses our rotation matrix times the default forward vector, the unit forward vector. And that way, if we change our rotation matrix, and then we call lookat with the position plus forward, it's going to be looking in a different direction. So basically, all this is doing is, when we update our transform, we're just taking what our existing rotation and position is and applying that rotation matrix by using forward directions. That way, when we calculate it, we just use lookat every time. which is essentially, if you look at the math for look at, it's like this. It's basically taking this rotation and multiplying it by the negative I. The reason why this is a problem is because we're flipping it back and forth because we're updating. Well, I'm not going to remove that completely yet. Let's see if we can. Let's do this. We'll do public virtual void rotate, and then we'll do float x, float y, float z, and we'll apply it. Actually, we're not going to. Now, I wonder, do we make this an aggregate? I think we do. Let's see what I do here. Rotate. Oh, that's interesting. So my rotate method in my prototype is this. Does this. Calls update rotation. And then it actually does this. Rotation is equal to rotation times Rock's math. XYZ. Which to me makes sense, but it might be a bit counterintuitive to how setting individual rotations are. So what I mean by that is we have this Euler. God, it's I swear, you guys are gonna have to just forgive me here. We're gonna do this, and we're gonna return. I'm gonna show you what I mean, and we'll walk through it. I'm just gonna write it out so that I can work it out in my head. So basically, we're gonna have X rotation, Y rotation, Z rotation. Copy those three. Y rotation, Z rotation. Make this a Z. This is Z. Y. Y. And that's it. When we update rotation, so this is where it's going to get. This is actually this is right. So we don't want to do rotation as Euler. And I think I agree with you, Faith. I'm not really positive that this extension method may be I mean, because even this seems misleading to some degree. So actually, let's reconsider. Let's get rid of that. Let's stick with our math-util version, which does the same thing. And then let's just use it like that. I feel better about that. So our Euler angles will always stay the same. They don't reset, they don't change, they're just values. And we don't have to update it until we call update rotation. Now, certain things are going to require us to update the rotation, but updating the rotation doesn't imply that we also update the transform. The transform only updates when we ask for the transform. So in this case, I feel This is how I feel. I feel like we should do this. But here's the thing, man. I actually hate this function, to be honest. Because this function makes us have to make a decision one way or the other. We don't want two ways of rotating something. Let's table this. Let's just table this right here. Let's just table it. At the end of the day, what we're going for, this is why it gets really tricky, because I think what I don't want to happen is this. When we apply rotations based on axis and angle and floats, are these x rotation, y rotation, z rotation, we're not updating the Euler angles, right? These Euler angles that we're using in our update rotation, we're just rotating something. And so we're going to update the rotation here. Then we would apply a new rotation, but this change wouldn't get reapplied to this. And so all of a sudden you have this problem where this is now out of date with the real rotation. And so the only way to make all of this happy is to really stick to one way of doing something, and that way you never have things that are out of sync. Does that make sense? I hope it does, because that's the problem that I'm running into, is that I'm trying to support too many ways of doing something. And it's costing me stability. And so I think what I actually want to do is get rid of this. I mean, our rotation is the constant here. You know what? Do we have a, we probably don't, but we could add it. I wonder if there's a, yeah. This actually doesn't even seem bad here. How much time do I have left? God, I have like 10 minutes, but we'll get to textures next time. But let's get this right. Let's try to get this right. So this is going to be, we're going to look back at our math util, and this is going to be basically the opposite port. This isn't bad at all. This is actually much simpler, I think. There's some quadratic stuff down there, but that's really it. And we're going to do, this will be, this actually, we're going to add it back. We're going to add back our math extensions. Public class, but we'll implement it first. So math util, and we'll do this. Public static vector 3 to Euler, and then we'll do Quaternion Q. Q dot y float z, q dot z float w, q dot w. And then float x2 x times x. This one looks like I already put care into it. Y times y. Float z2 equals z times z, and float w2 equals w times w. Float pitch. Wait, why 2 degrees? Oh, we're not doing degrees. We're hoping this is all in radians anyway. So let's see. math.a tan 2 is, we're going to do 2.0f times, actually, first term. This is always so freaking hard to, C++, man. It's like the most unreadable language ever. See if we can just get this term. T1 equals 2.0f times y times z okay, and this is term 2. Float T2 equals this. And then this should take 2 values, right? Yes. Okay, good. This is T1 and then T2. And we will just actually let's just do it like that. Give me a second. Float. And then I think we got to do a few more terms here. Float T3 is equal to negative 2.0f times x times z minus w times y. Here I go with the order operations again. Although that one looks a little bit safer to me than the other one. And then float T4 is going to be 2.0f times. I can actually copy and paste these, which is a little bit easier on me. Float T5 equals this term. All right. So let's talk about this then. Float y'all. I'm such a nerd. I'm sorry. Arc sine. And this is just going to be T3. And then roll is going to be also float math a tan 2. And it's going to be T4 and T5. And at some point, I'm going to start making some unit tests so we can ensure like these things do what they're supposed to do. Factor 3. Pitch. Y'all. Roll. Okay. Good. Good port. Good port. And then in our extension method here that we were going to add, we'll just have public static vector 3 return type, and we're going to have two Euler angles, I think. Sorry. And then this Quaternion and this. Now this gets a little tricky because I don't think that this thing breaks it up. I think this breaks all the angles into one. We'll see. I can't. You know, this stuff can be a bit of a brain buster. Because of the way that we're applying so let's actually just go in here and let's just do a test. Let's just do a stupid little test. And we can actually do this really easily by just removing that init and then just doing this. So let's say we have vector 3, v equals new vector 3, and we'll have what? What do we want to make this? Let's make it let's just add some random stuff. Let's is there a radians? No. We'd have to create one. Not a big deal. Let's just add some random values. Let's see. We'll do like float 2 rads equals, what is it? 180.f divided by math.pi. Right? Whatever. It'll be close enough. We'll do like 30 degrees. Maybe like 10 degrees. And then 2 rads. Like, I don't know, 50 degrees. Okay, so this will be interesting. Q1, we'll just use rocks math dot Euler v. Now, if you remember, this method applies each one of these rotations separately. Then let's do this. Vector 3 result. Let's we'll just do Euler. We'll do Euler. I'm not gonna stop. Euler equals Euler. Makes no sense. Worst spelling ever. Rocks math. Or we can do this. We can use our new extension method here. Okay, so what I'm guessing is that V and Euler are going to be different. Even though, intuitively, looking at the API, I think it would seem... whatever. I don't want this to do anything. Where is the rotate method? I commented it out and I shouldn't have, because I have it in the interface. It's fine. I'll have to add some stuff back to that interface anyway, I think. I'll add back this rotate and let's just comment that out so that it doesn't do anything. Both should be in radians. Yeah, no, both will be in radians. I just did radians here so that I could just use degrees here, because degrees are easier to think about in terms of like floats. So yeah, this is radians and this will be in radians as well. Everything that goes in and out of the math library is expected to be radians. Of course, this thing explodes. Why is dispose scene getting called? Is run getting called? Somehow? Yes, it is. Let's just add a read line there. That's fine. In fact, it is probably okay also that we call a init. Anyway. Yeah, so those are a bit different. Wait, did I do this right? No. No! I think this is what you were trying to tell me, Colt. But they're still different. However, if we do this, v.x, v.y, v.z, if we do this and we apply these as one rotation, this should be right. These should be the same. Are close enough. They are. They're extremely close. So, you could kind of see where we're going with this. Basically, what I'm going to need to somehow figure out how to do is how to create like an inverse of the other thing. If that makes sense. So this is going to give us basically this with individual components is the same as this. These are inverses. What's not an inverse is the Rock's math when we pass a vector 3, because the vector 3 actually splits the components into separate pieces, components, and then multiplies each quaternion together and returns a product. I think this is all we need right now to support our moving forward with Rock's objects and rotation. So let's stop here for today, and we can continue next time with textures. Anyway, I got to get to work, so I will talk to you guys soon. Peace.